Before looking at the next algorithm, let's take another brief diversion to understand another important concept of mathematics, that is, the concept of logarithms. Logarithms were discovered by a mathematician called John Napier in the 1500s. They've been used ever since by scientists and engineers to simplify calculations. Just as subtraction is the inverse of addition and division is the inverse of multiplication, logarithms are the inverse of exponentiation. For example, you probably already know that 2 to the power of 3 means 2 times 2 times 2, which is 8. We say that 2 is the base and 3 is the exponent. Therefore, the logarithm of 8 is the exponent, that is the power, to which the base of 2 must be raised in order to give us 8. We say the base 2 log of 8 is equal to 3. In the same way, if 10 to the power of 4 is 10 times 10 times 10 times 10, namely 10,000, then the base 10 log of 10,000 is 4. In general terms, we can say that if x to the power of z is equal to y, then z equals the log in base x of y. Strictly speaking, the base can be in any number, but in computer science, and particularly when we're using big O, we generally work with base 2 logs. Let's take a quick look at some more base 2 logs. If 2 to the power 0 is 1, then log in base 2 of 1 is 0. If 2 to the power 1 is 2, then the log of 2 is 1. If 2 to the power 2 is 4, then the log of 4 is 2. 2 to the 3 is 8, then the log of 8 is 3. We've seen that one already. 2 to the power 4 is 16, therefore the log of 16 is 4. And if 2 to the power 5 is 32, then the log of 32 is 5. Notice that each number here that we're calculating the log of is twice as big as the previous number, but each log is only 1 bigger than the previous value. So what does that matter? Well, let's take a look at our next algorithm, the binary search. The binary search is used to search an ordered list for a particular value. The binary search takes a divide and conquer approach. The target is compared with the middle value, and then half of the list is discarded. And this happens repeatedly until the target value is found. This is very efficient for large, sorted lists. Here's some pseudocode. It starts by establishing pointers for the bottom and the top of the data array by assigning its lower and upper bounds to a pair of variables, I-low and I-high. These pointers define the section of the array that the program is looking at, all of it to begin with. Inside a loop, these pointers are used to calculate the middle position of the array and to check to see if it contains the target value. If not, then, depending on the value in the middle, it effectively discards half of the list by redefining one of the pointers. It might redefine I-high to discard the top half of the list, or I-low to discard the bottom half of the list. This is an iterative approach to implementing a binary search, but this algorithm also lends itself to a recursive implementation because we're repeatedly solving smaller and smaller versions of the same problem. Either way, the time complexity is the same. Let's see how it works. Let's suppose our target value is 63. We establish the middle and compare it with the target value. The target value is bigger than 58, so we discard the lower half of the list. And then we do it again. We discard the top half of the list this time. And then we do it again. And we discard half of the list again. In this case, we've arrived at the correct value. And we chopped the list in half 3 times to do this. That's why it's sometimes called a binary chop. Let's do it again, but this time with twice as much data. We check the middle value. We discard half of the list. We do it again and discard half of the list. And again, discarding half of the list. And eventually we get there with 4 chops. Let's take a look at this graphically. Look at the data first. Notice that each value in the data column is double the one before it, and notice that the time values are increasing by 1 unit each time. You can see that the line climbs quite steeply to begin with, but then it begins to level out. That tells us for very large amounts of data the performance degradation isn't terribly significant. In terms of big O complexity then, doubling the amount of data requires only one extra chop. This makes the binary search very efficient for very large data sets, if the data is already sorted. The big O time complexity then is logarithmic, and we write O brackets log n. And what we're seeing here then is the classic chart for any algorithm which has logarithmic time complexity.